the ones we're going to try and do today using partial fractions, we're going to look at these other two bits that we've got in the formula book that we have. So we've got this one, which is 1 over a squared minus x squared, and the other one is 1 over x squared minus a squared. So we're kind of going through every type of fraction that you could possibly need to try and integrate. We're going to try and work out what all of these things possibly integrate to. We dealt with all of the ones that integrated to arc cos, well, integrated to arc sine and arc tan. Then they've got some of them that are going to integrate to r sine and r cos. Or maybe just r sine, actually.
R is not arc.
We just don't say the C bit.
Oh.
Yeah, but it still means the same thing. This one that we're going to look at actually integrates to something to do with a natural logarithm. But if you look at the formula book, it also could integrate to 1 over a r than x over a. So this is a reminder of the relationship that the inverse hyperbolic trigonometric functions can be expressed in terms of logarithms. And if you remember from the formula book, there's a little section where it says that like r sine of x is equal to ln of, I think it's like x plus the square root of 1 minus x squared, or something like, I can't remember it off the top of my head. I need the formula book for that thing. So it's interesting that these two things are kind of equivalent to each other, right? If this one I'm going to be proving it using partial fractions, I'm going to prove that this integrates to this using partial fractions. But there is another way that I could have proven that, and the clue is in the formula book page there. Yeah.
So the integral of the one that's up there.
Yes.
It's also 1 over a.
Yes.
Okay.
These things are equivalent to each other, like 1 over a r than x. And I think actually if I just quickly go back to this, when you integrate this, which goes to, we haven't done these yet, r cos and r sine, they are the same as integrating to ln of this and ln of this. And if you remember from elsewhere in the formula book, that's because there's an equivalence of r cos is the same as ln of blah, 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 okay? It's just, we looked at that in rollover beforehand. Now, we are going to do this using partial fractions, I said, but what do you think the other way would be that we could do this? Substitution, using what as the substitution, do you think?
X is equal to a than u.
A than u. X equals a than u. So if you wanted to do this in a substitution, you could let x equal a than u, but we haven't quite done like enough hyperbolic stuff. I mean, we probably have, but if you wanted to do a substitution, you could do a substitution because you would get a squared minus a squared than squared. Yeah, which is just a squared sec squared. And when you differentiate this is going to differentiate to, I think it differentiates to sec squared. It's either sec squared or minus sec squared with hyperbolics, but I think it just is, yeah, it's just sec squared. Okay, so you could do this with a substitution, but because we're actually in the chapter that is not on the hyperbolics, we're doing the non-hyperbolic integration so far. We're not going to do that with a substitution. But if you had to do a substitution, you could figure out exactly what it would be. So let's do partial fractions. We have 1 over a squared minus x squared. What do I need to do first of all?
Change.
Come on.
Factorize.
Thank you. 1 over a minus x, a plus x, which we now know is going to be a over a minus x plus b over, what am I writing b over x? A plus x. So you get 1 is equal to a lowercase a plus x plus b lowercase a minus x. So what do I need to sub in?
Minus a.
So x is equal to minus a. When x is minus a, you get 1 equals
b plus 2a. 2ab.
2ab. So b is equal to 1 over 2a. And when x is equal to a, you get
1 over
2a capital A. So you get 1 over 2a is equal to a. Probably shouldn't have used a, but hey, I've done it now. Not going to change it. So instead of integrating 1 over a squared minus x squared with respect to x, that is the same as integrating 1 over 2a over a minus x plus 1 over 2a of a plus x dx. Any suggestions of what I should do?
Put the 2a on the bottom.
I could put, yeah, technically the 2a will come on the bottom. I'd put them like this just because I think I can just take it all the way out to the front.
Oh, yeah.
Especially when you look at what you're aiming for, you've got a 1 over 2a there. So if we take it all the way out, we've got 1 over 2a, the integral of 1 over a minus x plus 1 over a plus x dx. Can these fractions here be integrated? Yep, into ln. So you get 1 over 2a. What does this integrate to? Almost.
Minus.
Good, because you've got to counteract this fact. The scaling will give you the minus when you have that bit. And that one's a plus ln of a plus x. So you get 1 over 2a. How do you combine these logs together?
Oh, the takeaway means divide.
The takeaway means divide, so it's going to be a plus x divided by a minus x. I've realised here we should have put a plus c. So we get ln, or 1 over 2a ln a plus x over a minus x plus c as required. Okay? Do you want to write that down? Do you need this booklet?
No, no.
Where is it? Why haven't you? You write it afterwards.
Yeah.
You do write it up
Yeah,
after.
yeah.
Okay. So yeah, when you can use partial fractions, why not? It's good for a proof.
Which of them are given in the formula book?
I'll give you a formula book now and you can have a look. Yeah. You've got this, and you've also got all of these here. Here, yeah, sorry, I was on the wrong page. So these are the ones we've just been using here. We've just done that one. So I'm imagining one of the other ones that comes up in your exercise is going to be to do this one, to prove it, prove the second one. Like I said, you could have proven that using a substitution. The substitution, remember the clues from the formula book, they tell you what the substitution is because you've already got what the answer is. So, yeah, what were you going to say?
Obviously, integrating one of them is not going to be a question by itself, but if it is a part of it, can we just go straight, like if we have 1 over a squared minus x squared as an like, let's say it's a number.
Yep.
Yeah. Can we just one step it?
Yeah, of course. Of course. This is only a proof, right? Everything that you've got here in the formula book is now what we call a standard result. So if it just says integrate this thing, you can just integrate it in one step. It's like exactly like what we did in the previous lesson, where you have to like make sure that you've got just x squared by itself. So if it had like a 5x squared, you'd have to divide everything by 5, find out what a squared is, and then root that, and then you just go through. It's exactly as what we did before, okay? Exactly the same thing about trying to make it look like that. So what we're going to do is we're going to do 2 examples, I believe. Is this the one that's the one I was thinking about? Yes, this is the crazy question. And this is one that's a bit more straightforward. So we're just going to now be doing partial fractions, but basically, yeah, just going to do like a bit more grown-up version of partial fractions. where if partial fractions comes up in further maths, it's going to be probably a little bit more demanding. So this is the partial fractions involving quadratic factors. So down here, I've got a quadratic factor, right? And I can't factorize this. So that's it. It's put down into these two factors on the bottom. They're not linear factors anymore. We've got a quadratic factor. So when you write as partial fractions, you have to ensure that you have the most general possible non-top heavy fraction, i.e. the order or maximum power of the numerator is 1 less than the denominator. So here, when you split it up, your instinct might have been to say, well, let's have a over x plus b over x squared plus 1. But this numerator bit here is not general enough because it might not be a constant on the top. It might be an x term, but it might not be just an x term. There might also be a constant term that you have there as well. So you always need to make sure that when you break it down, you make it as general as absolutely possible that you can have for this, okay? So for this particular thing that we've got here, we should look at this and we should ask ourselves a few questions. Okay, I get it, we're doing this, we know it's partial fractions. But if we didn't know this was partial fractions, we should look at this and say to ourselves, well, it's not reverse chain rule, okay? Definitely isn't reverse chain rule. The second thing I would then think to myself is it is not any of these kind of ones that we have down here either. So it means we've got to try and break this fraction down a bit. We've actually got to do a little bit more work to this. Now, this is probably going to take a while, so if you can try and keep on top of copying the notes as we go and tell me to pause if you need to. Otherwise, it's going to take us 5 minutes to write it up after. Yeah?
Can you go through the bx plus c bit again? Why
So if you wanted it to just be, usually it's just a number over something plus a number over something else, okay? If, though, it is x squared, it might not be a number on the top for it to be a non-top heavy fraction. There could actually just be something that's of 1 power less. So it can't just be, it could just be 1 power less, but it might actually end up just being a constant on the top. So you have to make it as general as possible and say, well, there could be no x's and there could just be a constant term. There could just be a constant term, there could be just x's and no constant term, or there could be a combination of both of them. So we try and make it as general as possible to come up with whatever that fraction will be. Yeah.
So if it's a x to the 4.
So if you ended up
you
with,
can have the bx.
let's say you had x to the 4 plus 1 and an x, and I don't know, whatever, 1 over that, it would break down into a over x plus bx cubed plus cx squared plus dx plus e all over x to the 4 plus 1. Okay? And this is where the five simultaneous equation solver is going to be pretty useful. So first of all, we recognize this is going to have to be partial fractions because that's the only thing we can do with this. So I will factorize the bottom and I get x squared plus 9. So I know that that is going to be the same as a over x plus bx plus c over x squared plus 9. The instinct of what your hand will want to do is just write b over x squared plus 9. So you really have to make sure when it's further maths, possibly even in maths, because we have seen this once before in maths, you have to stop yourself and say, oh yeah, I better make this as general as possible, okay? Now we get to this stage, I get 1 plus x equals a, x squared plus 9, plus x, bx plus c. Substitution is not going to do everything for you, though. I much prefer doing comparing coefficients for this kind of thing.
A has to be 0?
So A has to be...
Oh, no.
No,
No.
Because there's an x squared term over there.
So
1 equals minus 9a.
So what I would do, I would compare the x squared terms. On the left-hand side, there are no x squared terms. On the right-hand side, there is a plus b.
Okay.
Then I'm going to compare the x terms. On the left-hand side, I've got 1. On the right-hand side, I've got
B plus c. No, just c.
just c. So I'm just going to write like that. So c is 1.
Why do you have 2 little dashes?
No, it doesn't matter. I just did it to make it not look like it was mixing up with any of this stuff. I could have just drawn a line down here, just saying it's separate. So then we've got comparing the constant terms. I get 1 equals
9a.
9 A. Okay, now I've set it up like this. I've compared how many x squareds I've got to begin with. I've got no x squareds here at all. On the right-hand side, I've got ax squared plus bx squared. So I've just got a plus b lots of x squared. The x terms, I've got one of the x terms over here, and I've got none here, none here. I've just got c lots of x for that one, so c is 1. And then for the constant terms, I've got 1, and I've got 9a, no constant terms here whatsoever, because they've all going to be multiplied by x. Now, the reason I've set it up like this is to prepare us for what happens when we do the more complicated ones, because you may have a, b, c, d, and e. If you set it up where you put them all in the right place, you can then type that simultaneous equation into your calculator, and it gives you all of the values, as long as you've organized them carefully. But in this case, it's really easy for me to see that a is a ninth, so b must be, pardon?
8, 9.
Minus a ninth.
Oh, it's 0.
And c is 1. So that bit's all fine, right?
Is that how you'd recommend doing it?
I do recommend doing it in that way, yeah.
A ninth minus a ninth and 1. Yeah.
A ninth minus a ninth and 1, okay? So let's do a little bit more now. Now that we've got them written in partial fractions, I can actually say if I want to integrate 1 plus x over x cubed plus 9x dx, that's the same as integrating, well, a is 1 over 9. So if you want to, I'm sometimes in the habit of actually writing the fraction in the numerator. I just find it a little bit easier to factorize it out. So I've got a ninth x, then I've got plus minus a ninth x plus 1 over x squared plus 9 dx.
So we can take out a 9?
We could take out a ninth of everything, but actually what I'm going to try and hope that we might see this as, particularly what we've got in the question, is that we can see this as a series of 3 different things that are being integrated. Where are the 3 things that are being integrated? This needs to be separated, okay? So it's actually going to end up as being integration of integrating this, and integrating this. So it's 3 things that integrate. But why does the answer look like it's only got 2 things?
Oh, because the ln has a fraction.
Good. The ln is actually 2 things in disguise that have been put back into 1 thing, okay? So I'm now going to just split this up, and you can see now with my ninth here, I mean, you could have written it as 1 over 9x. So I've now got a ninth, the integral of 1 over x dx. Then I'm going to take this minus a ninth. So I've got minus a ninth, the integral of x over x squared plus 9 dx, plus the integral of 1 over x squared plus 9 dx. You see it now how we've got those different terms there split out from all those different bits.
No,
Are
you
we
know
allowed to do that?
So I want to know out of those 3 things, I want to know what each one integrates to, or what technique we use. Hamza, you tell me
the
one.
last one would be arctan something.
The last one is going to be an arctan one, correct. Ruhan, any of the other ones? Yes, the second one is reverse chain rule. Of course, the second one is reverse chain rule. And then the first one I'm not going to ask you about, because it's obviously...
Why are we allowed to do that?
Allowed to do what?
Split it into 3 different integrals.
Because if you integrated x squared plus 3x dx, what you actually do is you integrate x squared dx, and then you integrate 3x dx.
It's the same thing.
You just integrate them separately. That's how you integrate.
That is how you integrate.
We've
You
done
do
that
that.
last time.
It's just that we never write them separately. We just do them one at a time.
Yeah, the only reason I've written them separately here is because it's so complicated looking, it slows us down a bit, and it makes sure that we do put all the right numbers in all the right places. So I get a ninth ln x, no plus c required yet. Now this one's going to be a chain rule, so maybe what you might like to write is you might like to just pause for a second and say, okay, well let's rewrite this as x. Actually, I don't need to do that slowly. So it's going to be... So it's going to be another ninth of an ln x squared plus 9. Well, how are we going to scale that?
Divide by 2.
Going to divide it by 2, because when you differentiate this, you'd get 2x, but we only want there to be x, so you're going to have to half it as well.
That's what it
Yep. Then we have
is.
this bit. For this little thing that we've got over here, our value of a squared is 9. So our value of a is 3. Just turn back to the formula book.
A third arctan.
Is that what it is? Is it 1 over 1 over a arc tan x over 3?
X over 8.
Oh, okay.
Where did I get? Oh, because if you look on the formula page, or if you look on maybe like a previous page that we've got, things that look like that go to that. So we've got 1 over a squared plus x squared. So the a squared is 9, so we get that the a is 3. Yeah, don't forget my plus c as well. Now we just need to do some simplifying because they've got theirs looking like this.
So if we put the 9th in, like the powers in, using the learn rules.
Yeah, but do you want to put all of the powers in?
No, just the half.
Just the half? You want to put the half in?
So then we have a 9th in front.
Yeah, but look at the look at the thing you're aiming for.
Oh no, you want to do it for the first one.
You want to do it for the
change
first one.
squared.
So we need to change the first one
X squared.
to a squared. Is that going to work?
I'm not sure.
No, I think it's the half. If you put the half in and then put them together, then the half goes to the top.
So you mean like if you do a half
Times 9. Yeah, to move the half to the top. Yeah.
times a ninth times ln x squared, yeah. My brain wasn't going right there because you've put in
Yeah, that.
because you've put in a half, because you've put in a 2, sorry.
Yeah, we take out the
Because you've
half.
put in a 2, you have to take out a half to counterbalance it.
Yeah.
And then you get minus 1 over 18 ln x squared plus 9 plus a third arc tan x over 3 plus c. So we get
An 18.
1/18th ln x squared over x squared plus 9 plus 1 over 3 arc tan x over 3 plus c. So the clue in that question was the x squared. We had an x, so we forced it to become an x squared by putting a 2 in there, but counteracting it and making it becoming a half. The reason we were really doing that is because we wanted to have the common factor of the ln as an 18th.
What are we doing the opposite when you said we put the half on the outside and then counterbalance it with the inside?
Whichever way you want to think about it, you can either say I'm forcing it to go up to 2 and counterbalancing it with a half, but as long as you've got 2 and a half going on, it stays the same, doesn't it, the counter?
You know when you took the 1 over 9 outside,
Yes,
how come you didn't affect the last one?
I only took the 1 over 9 for this beginning bit,
And if you split up
and then for this bit here, I only took a minus 1 over 9 for this bit, and this bit here I didn't take anything out. This 1 over 9 that I have here is only applying to that. It's not applying to the entire thing that I've got. I've got no brackets saying that it's applying to the whole thing. Okay?
And then examine just write A equals this, B equals this.
Yeah, and then let's actually finish that off so we can say, I probably shouldn't have used capital letter A and B because they've got it here, but whatever. So A in this case is an 18th and B is a third. If you don't do that, it's not the end of the world, but it's better to do it. I always forget to do stuff like that. So I think I'm just going to do one more question with you, and then we finished chapter 3. But this one's kind of fun.
So is the question showing on in chapter 6?
So this is an example of a top-heavy fraction. So I've said here, if the fraction is top-heavy, you'll have a quotient. And when we say quotient, we mean like you get the extra bit that comes out, the whole amount that you have. As per pure year 2, if the order of the numerator and the denominator is the same, you'll need an extra constant term. So if the power is 1 greater than the numerator, you'll need a quotient of ax plus b and so on. So here, because the powers are the same as each other, you're only going to have like an a at the beginning part of it. If the powers were different, where maybe it said like this, 4x cubed plus x over x cubed plus x, you would need an ax plus b as the constant, not the constant, but as the quotient part of it. Then you would need a c over x plus a d over x plus 1.
Right.
because when you do that divided by that, it won't just be like here. That divided by that, I can see that a is going to be 4 because it's 4 times bigger than that one. Whereas for this one here, it's an x times bigger as well as a constant times bigger as well.
So when the power on top is the same for a higher degree, that's
Yes.
when you know it's going to have a...
Yes. Now what we have usually done in regular maths is we've done polynomial division. Lots of people feel comfortable with polynomial division. But I think we're better actually just to go, this is our thing. Let's just write out A, B, C, D, E, and let's just compare all the coefficients and then just set up some simultaneous equations. That's how I prefer to do it. But if you wanted to do algebraic division first, you could do, but it tends to be more time consuming. So the first thing it wants us to do for part A of the question is to express x to the 4 plus x over x to the 4 plus 5x squared plus 6 as partial fractions. So what do I need to do for partial fractions for the denominator? Factorise the bottom. What does the bottom factorise to? Sorry.
X squared plus 1, x squared plus 2, and x squared plus 2.
X squared plus 2 and x squared plus 3. And remember, it is a top-heavy fraction.
We don't factorise the top
Factors of 6 that add up to 5.
It's a pseudo-quadratic, isn't it?
So we won't factorise the top ever, will we?
No, we don't need to factorise the top. Now, this, we need to think, what will this look like? Okay, so we know it's going to be something, the quotient as the result of the division, plus something over x squared plus 2, plus something over x squared plus 3. What is this beginning bit going to be? A or ax plus b?
A.
I agree. It's just going to be a.
Because they got the same degree, right?
Because they've got the same degree. If the top part was x to the power of 5, it would have been an ax plus b. What's going to be on top of the x squared plus 2?
Bx plus c,
Good. It's going to be a bx plus c.
and then dx.
And then there's going to be a dx plus e here. Okay? So let's be really careful here. We've got, you won't, this will be much better, you'll see. So we get x to the power of 4 plus x is equal to, well, we need to have everything all multiplied up, don't we?
So a times by both of
So you get a by both of these things. Now we know what both of these things are. So if you want, you could write them like this, x squared plus 2, x squared plus 3. Yeah, let's just stick with that for now. Then we're going to have bx plus c multiplied by x squared plus 3. And then we're going to have dx plus e multiplied by x squared plus 2.
Oh, we could have put the big denominator there.
Yeah, here we could have put the big denominator because it might help us. Now, I don't know how good you are at this. I'm pretty good at just comparing the coefficients and doing the factorising and picking things out in my head. If you're not good at that, you either need to get good or you expand everything slowly. Now, I personally think we should just, I'm going to do comparing coefficients like this.
So you start comparing x to the 4.
Yeah, that's the one.
So if I compare x to the power of 4, the left-hand side I've got 1, and the right-hand side
That's just a.
I've just got a. Now I'm going to compare the x cubed terms. Well, I've got none on the left-hand side. Am I going to get any from this? How do I get an x cubed term from here?
Bx dx cubed
You just get a bx cubed, don't you?
and
And a
dx
d.
cubed.
And a dx cubed. So I'm going to leave a space and I'm going to put b plus d like that. So you can see I've got like a's, b's, c's, d's. Now I'm going to compare the x squared. So I've got no x squareds. Careful, how many x squareds do I have from the beginning part?
3a,
5.
5a. Wait, what?
Well, we know that it expands to that, doesn't it? So I'm going to have 5. I've got 2x squared, 3x squared. So I've got 5 lots of ax squared. How many x squareds do I have for b?
C?
Nothing for b, right?
Yeah.
So just c.
And plus e.
And plus e,
Yeah.
and plus e.
Oh,
I
okay.
don't like this whole columns thing.
No, but then we put it in
It'll help you. It will help you seeing it on the calculator.
Yeah.
We have
Doesn't look good.
One,
3b.
one on the left side.
So for the x ones, you get 1. How many x's here? None?
none there.
3B
3b.
Where are we getting 3b from?
and 2D.
2d.
And 2d, yeah.
Oh, yeah, 2D.
3b and 2d.
Do you have any constants?
Yes. Well, you always have to check. You can go all the way, can't you? So no constants. 6a,
We have 2E.
2e, and 3c.
Is that after 3?
Now,
No.
look, there are some ways of solving this, okay? It's actually not, we don't need to use the 5 simultaneous equation solver because we already know a is 1. And if you look at the x cubes and the x terms, you've just got a pair of simultaneous equations with two variables. You've got b plus d equals 0. Well, you could just say that 3b plus 3d equals 0, and you could compare it with this and you could do some subtracting. So if you want to, you can do simultaneous equations with them. And also with the x squared and the constant term, again, that's actually a 2-variable simultaneous equation. Why am I saying it's a 2-variable simultaneous equation? Because we know what a is. Now, if you want to, you could solve those by hand, or you could just use the calculator. It depends what you want to do. Like I'm guaranteed you're going to come across some questions that are harder than this one. So
B is 1, C is...
have you typed it all in?
No, I just not.
Okay, so a is 1, 5 unknowns.
The same thing again, B is minus 1, C is 1. I beg I'm right, because it's so sick.
A is 1, B is 1, C is
A is 1, B is 1,
Keep the 1.
C is 4,
Oh, shit.
G is minus 1.
D is minus 1,
Oh, they're both 0, that's why.
and E is minus 9.
It looks nice when you have whole numbers in the solver.
But remember, you could do this by hand.
I did it, man.
And you did it wrong.
Only C was wrong, got E right.
And that one was wrong because of C.
Because of C, E would have been wrong.
But when you wrote C, I got E. Straight away.
So Luke, do you now see why I wrote it in columns?
Yeah.
Just to make it a bit easier to type in the calculator. A little bit. Plus, it might have made it easier if you were going to do them by hand, to be able to do them. Now, I've not seen this come up in like a mark scheme before, but you can do it on the calculator, so I don't see why they wouldn't let you just do it on the calculator. Like, why not? You can do any other simultaneous equation on the calculator.
And main equation.
So now, let's integrate. So part B of the question.
One more days, I forgot what we were doing.
We're trying to integrate x to the power of 4 plus x over x to the power of 4 plus 5x squared plus 6 with respect to x, which is the same as integrating. Well, if you want, we can just do these.
Fraction first.
We could. I just think we can go straight into this, can't we? Oh, yeah. Oh, sorry. For part A, yes. For part A, and I'm not going to do it because I've already started the next bit. You actually need to express it in partial fractions. Okay? So I'm actually just going to go straight in and do the integration bit. So it's the same as integrating, and I'm doing it now. I'm writing it in partial fractions. 1 plus x plus 4 over x squared plus 2 plus,
Can we just do minus and then x plus 9?
but it wouldn't be, yeah, you could do if you want.
Minus x plus 9.
You want to do it like this?
Yeah.
Minus x plus 9, because obviously they're both negatives, so we put that as a plus, over x squared plus 3 dx. How many things is this going to integrate to?
5.
5.
5. And what kind of techniques will we be integrating them with, apart from the one?
There's two reverse chain.
2 reverse chain rules
One standard, 3 standards.
and 3 standards. What are the 2 of the 3 standards going to be using?
I don't want to stand.
There's the
Arctan. Yeah, arctan, because it's
Oh, yeah,
1 over a
sorry,
squared
yeah,
plus x squared. So
So what stands one again?
1 over a squared minus x squared. Other way, minusing and some subtractions. So it's going to be x plus, if you want, you can just do some of the integrals separately. So we've then got plus x over x squared plus 2 dx plus the integral of 4 over x squared plus 2 dx minus the integral of x over x squared plus 3 dx. Another minus, minus the integral of 9 over x squared plus 3 dx. If you wanted, you could have put the 4 out there and you could have put the 9 out there, whatever you want to do. I just did x there just to save a moment of time. So I get x. What does x over x squared plus 2 integrate to?
A half.
Half
X
learn.
squared plus 2. Yeah, learn it.
What does this integrate to?
Take the 4 out first.
2.
So what you might like to say here is your a squared is 2, so a is root 2,
So
and there's a 4 outside the front as well.
4 over root 2.
So you get plus 4 over root 2
arc
arctan
x over root 2.
x over root 2
We have a minus a half. And minus 9.
This one here, we can
over
see
root
that
3.
a squared is 3, so a is root 3. I know it sounds silly, but just having the a written there just seems to somehow make it kind of easier. And then we've got minus, there's a 9 over root 3 arctan x over root 3 plus c. Nearly there.
We can put the limbs together.
Put the lengths together and then that's it. So we've just got x plus a half ln x squared plus 2 over x squared plus 3. I mean, technically we don't need these modular signs anymore because we know that that's obviously positive, but whatever. And then here, you'll often see things just written as 4 over root 2 in the mark schemes and stuff because, I don't know, they feel like it's so much hard work, but technically you could rationalise that, couldn't you? So it's 4 root 2 over 2, which is 2 root 2. So you get plus 2 root 2 arctan. They often seem to just leave this as x over root 2 though. I don't know why they do, but they just do. And then 9 over root 3 rationalises to 3 root 3 arctan x over root 3 plus c. Now, because this was such a long question, I think I put the answer somewhere on the board so I could check it. No, it's fine. I think we got it right. So we're going to just do some practice on all these partial fractions questions, and that's us done, okay?
It's actually easier than it looks.